Good afternoon, everyone. Welcome to this presentation, and today we're going to talk about how we can map Mars using tethered balloons. Now, tethered balloons are a very interesting technology because they are a tried and tested technology. They were first proposed for both robotic and human missions, and you can see there an illustration of a rover traversing the Martian surface with the balloon above the dust that the rover elevates. And they have a lot of value. So why are they valuable? Well, first of all, they provide an aerial perspective. We are used to having two types of data when referring to Martian exploration. We have the orbital satellite data, which is all the maps and all the photos you've usually seen of Mars from space. And you have the high resolution rover photos, which make for cool wallpapers. Now, you have another thing that's very valuable is that you enable a third dimension when thinking about navigation. So you don't only have X and Y, you also have now a Z. It also allows for activity tracking near bases and mapping outside of the area of a base. You also have real-time scouting, so you can get a lot of data in real time, and it also serves as a communication relay. This is just an example. If you go into a valley and you don't have a direct line of sight to the communication antenna on base, you may not have communications. But if you have a balloon, you can see that you have that elevated point which can serve as the communications relay. And it also serves as a search and rescue. So a cool thing about the tethered balloons is that they are very versatile. So you can add high visibility for safety and easier search, and they are simpler and low cost. Additionally, they rely on passive lift. This means that you really won't have to worry about fuel consumption beyond inflating or deflating the balloon. They were first tested in 1988 in Antarctica. As you can see there are some pictures. And they were also tested in the Arctic in the year 2000 and in 2022. And the second technology that will make this possible and in which the study focuses on is simultaneous localization and mapping, also known as SLAM. SLAM is a very interesting technology because it encompasses a bunch of smaller technologies. There are a lot of techniques to know where we are and to characterize our environment. So there is stereo, monocular, multisensorial, LiDAR, a bunch of different ones. We will be focusing on multisensorial. As the name indicates, it uses a bunch of different sensors so we can have different types of data work together to build a comprehensive image. And it's vital for exploration and mission planning. Now, to explain the stereoscopic effect, I want to make a little exercise with all of you. Try to extend your hand as much as possible, or your arm as much as possible. Give a thumbs up. Close one eye. Close the other. Did it move? Yeah, it moved. Now, do it closer to your face. Did it move?
Yeah.
And it moved a lot more.
It appeared to move.
It appeared to move, exactly. That's the point. We now know that there is a relationship between the distance of an object and the differences that we perceive. So if we have a pair of two cameras that acquire a picture at the exact same time, and we have a computer to check for the smaller differences that we may or may not see, because computers are a lot better at that, we can actually estimate a depth. And if we know our coordinates, and we know the distance to a point, we can create 3D vectors. And we can repeat this process over and over and over until we obtain a map. Of course, balloons aren't stationary. You have two different types of movement. The first one, of course, is rotational movement, because the balloons do rotate, and the translational movement. For rotational movement, we can have an inertial measurement unit which will detect these rotations, and we can counteract them actively with brushless motors. This is called active stabilization. We can keep the platform level this way. We have translational movement. It's very hard to maneuver on flight the balloon, so what we will do is something similar to here. So as you can see, we have a cross, which is our reference point, and by knowing how far we are from that cross, we can know how much the platform moved. And to account for height, we will have a laser altimeter. Now, this is the 3D design for the payload. we have the Raspberry Pi 5, which will serve to register all of this data and coordinate the different sensors. We have the IMU, or what we previously discussed, the pair of stereo cameras. We have them in 4 directions to have an almost 360 degree field of view, and motors for active stabilization. And in the bottom part, we have the monocular camera and the laser rangefinder. Now, how does this actually look in practice? This is a 3D map that was taken of a simulated patch of Devon Island. So to create this map, what we did was we first downloaded a patch of topological data from Arctic DEM, specifically of Devon Island. We then simulated that environment to actually have the features that it would usually have, ran the simulation with the payload, with the process as previously discussed, connected all of the 3D vector points that the software created, and compared the 3D models. So as you will notice, the closer we are to the center, we see a lot more blue, which indicates less error, and a lot less red and yellow, which indicates a lot more error. This is the nature of stereoscopic imaging. As you saw, it's a lot harder to gauge accurately how far something is, well, the further it is and the less differences there are. So for future work, we will construct a physical model for actual field testing, tested at the HMP on Devon Island, and finally design, develop, and propose a flight model for Mars. And this is where we are going to test it. And to end, I just want to remark how important it will be to have reliable mapping data, and that stereo and SLAM could very well change how we think about future robotic and human exploration. Thank you a lot for your attention.
Thank you. You have a very good job. So as I transition to the next speaker, you can ask some questions.
Okay.
For your balloon, are you thinking of hot air? And what hot air source would you have? Or are you thinking more of a helium/hydrogen type balloon? And what fuel source would that be limited to?
It would be limited to hydrogen, since it's less dense than the Martian atmosphere.
And there's no oxygen on Mars, so it can't go Hindenburg on us.
Right. Exactly.
Considering the very low density of the atmosphere of Mars, does your balloon have to be 10 times the volume to get an equivalent amount of lift compared to the Earth? Although I'm kind of curious there.
Yes, so it would have to have a lot more volume to reach sort of the same amount of lift than here on Earth.
It's sufficient to support your equipment and the balloon mass, etc.
Yeah.
Have you done the calculation?
Yeah, the payload will be designed to be as lightweight as possible, so we won't be using, we will reduce weight as much as we can to avoid those situations. Any other question? No. One last? Okay, sure.
Thank you.
Thank you.
Leonardo.
Thank you. So the next